Okay, hello out there. This is Mr. Leader. This is Advanced Pre-Calculus, Section 4-1. This is stuff on angular and linear velocity. I'm just going to go over problems 105, 107, 109, and 110 because some people were kind of confused in class. I'm going to try to be a little more clear and to the point, so that you could review this. So these are all linear and angular velocity problems. So we'll first look at number 105. Okay, so let's grab this problem. And with these types of problems, it's useful to draw a picture of it. So in this case, an electrical hoist is used to lift a piece of equipment 2 feet. The diameter of the drum is on a hoist that is 10 inches. So what you have going on here is some kind of hoist on a wheel, okay? And the diameter is 10, which means its radius is 5. And it's pulling up something, whatever it is, and it's pulling of the diameter of the drum on the hoist is 10 inches, and the drum must rotate to lift a piece of equipment that is 2 feet, which is 24 inches, okay? So this is 24 inches. This is 5 inches. We're going to use the formula, find the number of degrees. So even though they're asking for degrees, we're going to find theta first in radians. So theta, we have a formula, theta is equal to S, which is the arc length, over R, which is the radius. So in this case, this is a pretty easy problem because S is just 24, because when you roll this wheel around so many times, it's the arc length that it's going to travel is 24 inches. It's going to wind, this cable is going to wind itself around this wheel 24 inches, so it's going to go around that. So this number is S, which is the arc length. So I'm just going to put 24 up here, and I'm going to put R, the radius, which is also in inches, down here. And since theta in radians is the ratio of S to R, okay, I just plug that into my calculator and I get that's 4.8. That's in radians, okay? If I want to change that into degrees, I multiply that by 180 degrees in pi radians, and I'm just going to do that on my handy dandy calculator right here as it loads. Okay, and
Did you happen to pick up any more stats?
okay, so when I multiply, so I'm just going to take my calculator, I'm going to multiply 4.8 times 180, and I'm going to divide that by pi, and I get that answer is 275.2 degrees, 0.02 degrees approximately. Okay, so that's number 105. Let's go to the next problem. Okay, next problem is 107. Linear speed. We did this one in class, but I'm going to do it again for you. So grab this one. Here we go. Linear speed. So linear speed is how fast something is moving around around a circle, but it's also just distance traveled versus time. So the formula that we have for linear speed in the book, they use V, and that's equal to S, which again is the arc length, over time. So in this case, we have a satellite in a circular orbit, 1250 kilometers above the Earth. The Earth makes one complete revolution every 110 minutes. That's your time. What is its linear speed? So S, in this case, we have another formula that says that the arc length if we know that, let's just go back a minute. If we know that theta from the last problem, or what I've told you, is S over R, that means if I'm solving for S is equal to R times theta. That's a formula for finding the arc length when you know theta in radians, all right? So in this case, velocity, S is going to be R times theta. Well, if the satellite is above the Earth and the radius of the Earth is 6,400 kilometers, and I add the height of the satellite above it, which is 1,250 kilometers, so that satellite is going to be buzzing around here at 1,250 plus 6,400, which is 7,250, 7,250 kilometers above the Earth. That's the radius. Theta, it makes one complete revolution. Well, one complete revolution in terms of pi, that's theta. So one complete revolution is 2 pi radians, okay? And that would, this times this, R times theta is going to give me S. And if I take S and divide it by if I take S and divide it by T, I get the the linear speed, okay? And so V for velocity, velocity really implies direction, but we're calling it V anyway. So I'm going to divide that by 110 minutes, and if I take these numbers, I multiply them together using my calculator, 7,250 times 2 second pi. I'm going to divide that by 110 minutes. You should keep the units on here, okay? And that means that this satellite is traveling at 414, whoops, I see a mistake. That should have been 7650, not 7250, right? 1250 plus 6400, that should be a 6 right there. So I'm going to change that into a 6. Let's try that again, okay? I'm going to go 76,7,650 times 2 second pi divided by 110 gives you 436 about 437 kilometers per minute. And they didn't specifically ask you for units, and since these down here, since these down here are in minutes and this is in kilometers, radians, you don't really have to put any units, so that would be about 437 kilometers per minute. There's problem number 107. Okay, moving on. Problem 109, which gave some people some headaches. Let's look at this one. Mechanical engineering. So, gonna come here. I am going to partial, grab the problem. Oops, I need to try that again because I didn't get all the problem. Let's go down again. Okay, so now I'm gonna place this one in into a new window. Here it is, okay? And so in this case, what you have is a same type of problem. You have a circular blade on a saw that has a diameter of 7.5 inches and rotates 22,400 revolutions per minute. Find the angular speed in radians per second, okay? So angular speed, which they call omega, angular speed is how fast is something rotating. So it doesn't matter, this is an omega that I'm trying to make, it's how much does it rotate in some certain unit of time, okay? So in this case, they give us revolutions per minute. They want the angular speed in radians per second. Well, we know that it's doing 2 pi radians every revolution. So it's going 2, theta is going to be 2 pi radians per 1 revolution, but it's doing 2,400 revolutions per 1 minute. So notice here, this cancels out, okay? This is going to give me, each revolution I get is 2 pi radians times 2,400 of those revolutions every minute. Now I have theta, I have my time, and I can just multiply. And I'm going to go get my handy dandy calculator over here. 2 second pi times 2,400 divided by nothing, right? Because I don't have to divide by anything because it's just 1 minute. And I get 15,079. That's radians per, what do they want? They want angular speed in radians per minute. What I would have to do is take that answer. They want radians per second. So we know that using a conversion, there's 1 minute or 60 seconds in 1 minute. And now I could cancel out my minutes like that. So if I take that answer and divide by 60, okay, I will get 251.33. That's radians per second. Okay, so that's how you do that one. Find the linear speed of the saw teeth. So again, if I know it's going 251, what do they want then? In feet per second. So I have radians per second. I know that it's going, again, I know that V is equal to S over T, okay? And I know it's going, this is theta over T. To find S, given theta over T, all I have to do is take that number and multiply by the radius, right? Because S is equal to R times theta, and this is thetas per second, if you will. So S is going to be the radius, which is 7.5 inches. They want feet per second, so we're going to have to change that into feet. 7.5 inches times 251.33, okay? That's radians per second, okay? And they want this in feet per second, so there's 12 inches in 1 foot, so I'm gonna have to take that answer and divide by 12 inches in 1 foot. And then if I cancel out the inches, okay, I'm gonna be left with feet per second for my S. Okay, so I'm going to take my calculator again. 7.5 times 251.33. And I'm going to divide that answer by 12. And I get that it's going, that saw blade is going 157.08 feet per second. Okay? I think we did that right. Let's make sure that they give me the messed up, okay? Because this is supposed to be, I make mistakes, that's supposed to be the radius, not the diameter, so that should be 3.75. So what happens is I take that answer, divide it by 2, because I'd be multiplying my smaller by a radius, not by the diameter. So if I take 157.08 divided by 2, I get 78.54 feet per second, which is pretty fast. Okay, next problem, moving on. Sorry about the mistake, I'm trying to go fast. next problem. Let's hide this. Number 110, which I did in class, and someone put on the board, but I think between their explanation and mine, we kind of got hung up. So angular speed, we're looking for angular speed. So again, similar type of the problem to the last one, but we have more conversions to make, okay? We have a computerized spin balance, machine rotates 25 diameter, 480 revolutions per minute, and the diameter is 25 inches. So rather than use the diameter, I'm going to say that find the road speed, which is actually the linear speed at which the tire is being balanced. Okay, so if the diameter is 25 inches, that means that the radius is half of that, which is 12.5 inches. Okay, and it's doing 480 revolutions per minute. Okay, and there are 2 pi radians, okay, in each revolution. So this is theta. This expression on the top is revolutions, because you're going 480 revolutions times 2 pi. That's the angle that it's rotating through. So, so that, and then per minute, that's the time. So we're using the formula V is equal to theta over T again. So this over here is theta on the top, because it's 2 pi times 480 revolutions. So it's going around the circle 480 times every minute, so the time is 1 minute. Then, so now I'm going to have the, that's, I'm sorry, I want R theta. Okay, so I know theta, okay, but R is 7.5, so I'm going to have to take that and multiply it by R, which is 12.5, to find my S. So R theta is S. Linear velocity is S over T, and S is R times theta. So, so that's how that works. And so now this is in inches. So this is going to give me the linear velocity in inches per minute. Look at the units they want. They want miles per hour. So I'm going to take 12.5 inches, which is my radius. This is theta. This big expression here is theta. And T is down here. Okay? So that's, I have S over T, but I need to do some converting into miles per hour. So I know that there are 12 inches in 1 foot. And I know that there are 5,280 feet in 1 mile. And this is in minutes. I need hours. So I'm going to multiply that by 60 minutes in 1 hour. Okay? Now what happens is all this stuff cancels out. Minutes go away with minutes. Revolutions go away with revolutions. Radians, you don't really need to cancel that because radians don't really have units. That's just to indicate that. Inches, cancel with inches. Minutes, 60 minutes. Oh, that should say mile. That's where I got confused. Feet, cancel with feet. And what I'm going to be left with is miles per hour. So if I multiply all that stuff on the top, I'm not going to do it because with my calculator, I get that it's moving at approximately, and divide by the stuff in the bottom, I get 35.7 miles per hour. Okay. And then for the second part of the problem, at what rate should the spin balance machine be set so the tire is tested for 70 miles an hour? You could just set up a proportion. Since this is a linear relationship, I can say that 35.7 is to 70 as 480 is to X. So cross multiplying and divide, I get, I'm just going to do that on my calculator really quick. I'm going to get 35.7 times 480 divided by 70. Whoops. I'm in a rush. I wanted to multiply 70. Bell just rang. 70 times 480. Cross multiply and then divide. Divided by 35.7. And I end up getting 941.17 revolutions per minute. 941.17 revs per minute. Okay, so I hope that clarifies things. That's those problems. You can review them, come and ask me questions. And thank you and goodbye.